Good afternoon. I think we're going to get started. Peter and I want to thank you for attending our talk and for the opportunity to come here and to speak, to share a little bit of our experience with you. We're excited. We hope you enjoy it. We'll be talking about monkeys in lab coats, or breaking things on purpose in production, how we do automatic failure testing, and how we made it work at Netflix.
So as the professor on stage, it's probably fitting for me to begin with a quote by Aristotle, a quote, or a cliche, if you like, that I'm sure you're familiar with. The whole is greater than the sum of its parts. And we've probably seen this quote interpreted in various ways in different contexts. But the way I'd like us to interpret it in this context, because this is a talk about collaboration and how it can work, is that if a collaboration is done well and carefully, we can walk away with it with much more than sort of the mere totality of what we brought to it. That is to say, collaboration, when done right, can be a multiplier. Oh, one other point I'd like to make, and this might be sort of a controversial point, is that it seems to me, from my experience, that the further apart you begin, sort of the further you walk from two poles to a middle where you meet when you do a collaboration, the richer the opportunities for multiplicative effect. I hope we'll convince you of this today. And so just to give you an idea of just how far apart Kolton and I began, let me give a little bit of introduction of us. So I'm Peter Alvaro. I'm an assistant professor of computer science at UC Santa Cruz. Before that, I was a PhD student for many years at UC Berkeley. And before that, I was a software engineer for about 8 or 9 years in industry. When I left industry, I swore I'd never go back, so never say never. Something that I have to come clean about for this crowd, even though it's a little bit embarrassing, is that I'm really a prototyper at heart. I'm so all about the idea that once I convince myself that the idea is possible by constructing a prototype, I'm not that great at finishing it. I wish somebody else would take care of that mere engineering. And so this collaboration was quite a learning experience for me, being forced to push stuff all the way through.
So hi, my name's Kolton Andrus. I cut my teeth on failure testing at Amazon. We were on the retail website availability team, and I had the opportunity to build a failure injection system there to help us become more resilient. After that, I went to Netflix. I figured if there's a place that you can go and learn more about failure testing, Netflix has got to be the place. And indeed, it was. But when I got there, I found that there was some opportunity to improve. I had an opportunity to contribute and to build kind of the next generation of the monkeys there. With FIT, a failure injection service. At both companies, I've had the privilege to serve as a call leader or an engineering crisis manager, someone who's nominated to manage large-scale incidents, to be on the phone, to help resolve it, to figure out what's wrong. And truth be told, I kind of miss getting paged at 2 in the morning. There's a little rush that comes with, oh, this is broken for everybody, I can fix it.
To further emphasize how different we were at the beginning of this collaboration, I think it's worthwhile looking at the figures of merit for our respective communities. How does an academic versus a practitioner measure whether they're on the right track, whether they're achieving success? And so as an academic, one of the most important sort of KPIs is the so-called H-index. Can I see a show of hands who knows what an H-index is? Hey, some people know what okay, so my H-index is K if my K most cited papers have been cited at least K times. Yeah? So it's sort of a slightly sophisticated retweet count. We're also measured by our ability to do research in the future, which really just comes down to dollars. It costs about $500,000 to mint a PhD. So how many millions have you brought in from grants, from gifts from industry, and things like that? And arguably, maybe most important, how high is your department ranked among other departments in the United States in terms of the quality of research that you're doing? So 3 different KPIs that collectively tell me how I'm doing as an academic, measured very narrowly based on my impact on other academics.
So it's just a popularity contest.
It is a popularity contest, and that's why it's important to remain popular, because popularity contests work out great for popular kids.
So what do we care about in industry? We have some hard metrics you're probably familiar with that measure whether or not we're winning, whether we're successful at what we're trying to accomplish. The measure of availability, however you slice and dice it, is an important one. The number of nines that you're able to serve to your customers. To me, we're winning if we have 4 nines or 5 nines of availability. If our customers essentially never understand that we're down. Then what happens next is the number of incidents. So sometimes it's also the severity that goes into the overall metric, but if you're on calls all the time, if things are broken all the time, no one's happy. Customers aren't happy, management isn't happy, engineers aren't happy. And lastly, and I think most importantly, I'm lazy. So if there's something I can do to reduce my operational burden, if there's something I can do so that I don't have to firefight in the middle of the night, then I'm all about that. So, kind of an unlikely team, an academic and an industry collaborator. So how did this come to be? So I want to provide a little backstory here, but I also want to provide a little context. So before we dive into how this came to be, let me tell you a little bit about FIT. So I mentioned FIT, or Failure as a Service, is what we built at Netflix. And it enabled us to do this collaboration because it provided a couple of key things. FIT is built to be application layer failure testing. And so what it enabled us to do is decorate individual requests as they entered the Netflix ecosystem and follow that request as it traveled its path and break anything we want along the lines. It integrated with our tracing infrastructure so we could see what happened. And it let us, that fine-grained granularity allowed us to control the blast radius or the potential for who we were going to impact. So we could start, and we often did start, by testing a single user, mine usually, or a single device, maybe the Xbox I have, maybe my browser. And as we saw that that worked as we expected, then we built upon that. We increased the failure scope. So then we might run for a percentage of customer traffic. Then we might run for 10% of customer traffic. And I find that the successful failure tests that we ran, our goal was always to run it at scale at 100% in production. So you may not have known this, but we've done this several times, and probably while you're watching Netflix. Maybe it manifests as the ratings go away or things change, but we were able to do this successfully. The last bit I'll say about this is we built it as a service. We wanted other people to be able to extend this idea and to build upon it in ways that we didn't anticipate. And so we provided a service API, and we allow it to be extended upon. Ali is giving a talk tomorrow about CHAP, which I'd recommend that you attend. But CHAP is built upon FIT. So the infrastructure and the failure service that FIT provided allowed them to do these more interesting experiments on top of it. So great, FIT works great. We went out, we were able to use it to help improve the reliability of both the edge services that we owned and Netflix as a whole. But it's primarily a manual process. We would work with engineers, we would sit down with teams, we would talk about what could go wrong, and we would work through those exercises. Now obviously, we would prefer something that would scale without the number of engineers involved. So surely there's got to be a better way. And the opportunity here was for me to be able to go out and to look for people smarter than I who might have figured out this problem. And lo and behold, I'm at my desk. It was holiday break 2014. And I'm watching this video from this interesting looking professor guy. And he's talking about lineage-driven fault injection. And I listen to this talk and I go read the paper. And it's very interesting. I thought, aha, this is it. This is a way that we could go about doing failure testing for everyone automatically. So how do you get time with a professor? Well, one, you blind email their cs@berkeley.edu email address, and you say, hey, I read your talk and I saw your presentation. I'd love to chat more. I'll come to you in the city and buy lunch. Would you like to get together?
And truer words were never spoken. Because grad students, and I was actually a grad student at the time, grad students and professors are extremely lazy and extremely hungry. So you know, buy me lunch sometime. So Kolton came to the city and he bought me lunch. It was a really nice lunch. And we had a great talk. I shared some of my ideas. I went a little deeper into LDFI than I did in the paper, right? So Kolton learned some things. And Kolton told me more about the Netflix infrastructure than I had ever known or maybe even wanted to know. And it could have ended there, you know? That would have been an example of like an additive collaboration where we both come to the table with some things we know and we trade a couple things. Kolton goes back to Netflix knowing a little bit more about the academic take on how to automate failure testing. I go back to academia with a little bit more street cred. Next time I write a paper, I might have a case study that looks a little bit like Netflix and has a little bit, you know, looks like a realistic use case, right? But I know from experience that this kind of additive collaboration doesn't really move the needle much. It doesn't really advance the state of the art. It would be additive, right?
So fast forward a couple of weeks, Peter calls me up and he says, hey, I've got a crazy idea. What if we built this? Like Netflix is a hip place. They're open to taking risks. Do you think that they'd let us go build it? And Netflix is pretty good. One of their core values, freedom and responsibility. If you have the freedom to make choices and to take risks, and you're responsible for the outcome. So I went and I spoke to my management, and they grilled me a little bit on the value and how it would translate into real value for our customers. But in the end, we were able to convince them. And so Peter came and was my professor intern for a summer as we went about exploring this idea.
And just to pop up a level, I made a big deal in the very beginning of this talk about how different we were. This was really a point of convergence for us. At least within Netflix, the responsibilities and freedom of engineers look very much like the story in academia, right? In academia, we don't have any bosses. We're completely free. But as Milton said, we're free to fall, right? Any chance we take, any gamble that we take, all we're putting on the line is the success of our career. And so both of us, a little bit concerned about this responsibility, did some due diligence before we did our collaboration. We both wrote down individually what we wanted to get out of this summer, how we would know if we had succeeded. And when we compared notes, we were delighted to find that we had written more or less the same things. So for my part, it's really important to me to take these ideas that we've developed in the lab, these idealized models of reality, and to provide evidence that they match reality, right? Equally important, we want to be able to show that our algorithms actually work at real-world scale. Because as many of you know, or maybe don't know, in the lab, we don't have large-scale systems, right? We're forced to simulate them. And we're always afraid, maybe we're quiet about it, but we're always afraid that because we're creative people, we're inventing and solving imaginary problems rather than addressing real-world ones, right? And then arguably most importantly, when I returned after that summer to the lab, I wanted to return with a treasure chest full of real bugs from real systems that wouldn't have been found without our work. And it turned out that Kolton had more or less written down the same exact things. Oh, right, so now it's time to dive down and talk a little bit about the idea behind LDFI that so attracted Kolton. What is the main idea and how does it work, right? Consider a microservices-based company in which a large number of services that are independently maintained interact. And you ask, well, what does it mean for a user to have a successful interaction with something like that? That might involve connecting some large number of services, let's say like 100 services. At the end of the talk, we'll see an example in which a single interaction actually involves cooperation of 100 services. And in order to have confidence that those interactions work correctly under fault, to a first approximation, we would need to see what they do under every possible combination of faults, right? So if we have 100 services that are cooperating, at least back of the envelope, we have to consider the set of all subsets. That's 2 to the 100 different experiments that we would need to perform to cover the space exhaustively. That's like a 1 with 30 zeros after it, right? So that's obviously not going to work. Now, we might not be ambitious. We might say, well, we're going to consider what happens when one service falls down during an interaction, and that's tractable. That's like 100 executions. You imagine that these experiments are going to run order of seconds, right? But if we turn the dial up to 4 faults, we're looking at 3 million executions. If we consider up to 7 faults happening, we're looking at 16 billion experiments we would need to run. This isn't going to work, right? We need to do something smarter. Now, an approach like Chaos Monkey, which was pioneered at Netflix, says, well, it's hard to do much, like when you do random, you certainly don't hit the worst case, right? So we could flip coins. And that's pretty much what Chaos Monkey does. You imagine there's this dartboard characterizing the space of possible experiments under failure. And Chaos Monkey randomly picks failures to inject. Some of them are fairly deep in the space. Some are quite shallow, right? Now, the advantage of random search is that it's very easy to automate, right? Random search works equally well on any infrastructure. You don't need to tune it to an infrastructure. Unfortunately, random search doesn't work very well on any infrastructure, right? And certainly, it doesn't give us any notion of coverage. Like, let's say there's a point out here where there's a known bug. What are the odds we're going to hit it with a dart? And can we ever hope to blacken this dartboard by stabbing into it at random? Right? The sun will be burnt out before we finish. an approach that's more popular in practice, one that Kolton already alluded to, that the users have fit to, is to exploit the intuition of the actual service owners, right? In a service-oriented architecture, different teams manage different services. There's quite a bit of deep knowledge on a service-by-service basis. So you can exploit that knowledge and do a sort of engineer-guided walk through the fault space, achieving much better coverage, exploring some deep faults and some narrow faults. But unfortunately, unlike random search, this approach is fundamentally unscalable, right? It's only as good as the intuition of the programmers, and it only scales with humans, right? So the main idea, there's kind of two main ideas behind lineage-driven fault injection. The first is that, fault tolerance is really just redundancy. Like definitionally, fault tolerance and redundancy are like synonyms. A system is fault tolerant precisely if it provides more ways to obtain some good or expected outcome than we anticipate there will be failures in an execution, right? So if we could spot the redundancy in a system, we could know what faults it can tolerate, or conversely, what faults would make it fall down. But how do we know redundancy when we see it? So another key idea of LDFI is that instead of starting with this really open-ended question, like this is how we do verification with model checkers. We say, could a bad thing ever happen? Let's just check every state in the state space and say that a bad thing never happens. When the state space is large, this gives us very little direction about how to carry out the search, right? A better idea is to begin with some good outcome or some representative class of good outcomes and say, exactly why did the good thing happen? And could the system have made any wrong turns along the way? The answers to those questions are going to turn out to be the much smaller set of faults that are going to be interesting to spend resources injecting, okay? Now, I come from a database background, and in the database world, when we think about how we explain why things happen, a really popular tool is provenance or lineage, a succinct explanation of the data and computational steps that led to some outcome. So let's take a look at lineage a little bit more deeply. Let's consider a good thing that happened in some execution. You imagine it's a system like Cassandra. The good thing that happened was that we did it right, and it was acknowledged, and it was durably stored. We say, well, that's good. Why was it good? So we start to unroll it, and it says, well, the right was stable because it was stored on some replica, replica A. But that's not the only reason it was stable. It was stable also because it was stored on another replica, replica B. It's redundancy, right? Okay, but we continue asking this why question. Why was it stored on replica A? Well, because the client broadcasted it to replica A. But there might have been more than one broadcast. There might be more than one reason it's on replica A, right? So when we're done recursively asking why questions, we're left with this graph that essentially shows us how the good thing happened and what redundancy there was in the system to support it, right? So now we can start to ask, okay, could I make any cuts in this graph that could prevent flow from the leaves to the root? Right? So naively, the replicas could fail, or the broadcast could fail. That's 4 things that could go wrong. So that's 2 to the 4 experiments that we could carry out, 16 experiments. But it's easy to see just looking at this graph that not all those experiments are interesting, right? Like it wouldn't be interesting to fail these 2 things because I can see that there's a path from leaf to root, right? By contrast, those 2 failures look promising, right? Because they block the flow. Okay, well, how do we take this kind of human intuition staring at a graph and turn it into a problem that a computer can solve efficiently, right? Well, we can just sort of mine out the individual sort of subtrees that are themselves sufficient to produce the outcome. Like a client could broadcast something, it could get to replica A and it would be stable. We say, okay, well, what would it take to break that subtree? Well, we could crash replica A or block broadcast 1. We say, well, but wait a minute, there's more than one subtree. Here's another one. And to break the whole system, we'd have to break both of those subtrees. So we'd have to do this and this, yeah? And so we just keep turning the crank, mining out these subtrees until we've exhausted them all. And along the way, we've consed up this Boolean formula, which you may recognize as already being in conjunctive normal form. So we could just take this formula as it is and pass it to an efficient off-the-shelf SAT solver and say, are there any solutions to this formula? The solutions to the formula are going to represent faults that are interesting to inject, that could break the flow. For example, here's a suggestion. Interrupt these 2 broadcasts. Okay, so what we get out of this, and indeed what we wanted, was every time we cast a dart into this dartboard, we don't just cast it randomly. We cast it into a region that we can prove based on our model is interesting, could break the expected outcome. But more importantly, every time we cast a dart into the dartboard, it casts a shadow over the search space that we never need to explore again. We add constraints to our model, and our solution space diminishes quickly. So, at a high level, when Kolton and I began our collaboration, I said, Kolton, here's the recipe for LDFI. It's easy. You have all the pieces. It'll be a snap. You start with a successful outcome and work backwards. You ask, why did it happen? And this recursive process of asking and answering why questions gives us a lineage graph, which we can efficiently encode into a CNF formula, solve. The solutions represent hypotheses that we should go experiment with using our fault injection infrastructure. And when we run an experiment, one of two things happens, right? We find a bug, in which case success, or defeat, or something. I'm not sure. It depends how you look at it. Or we find evidence of additional redundancy and keep going around the loop until we run out of moves. So we're either going to end up at a bug, or we're going to run out of moves and say we've covered the space, everything looks good.
Great. So we've got an approach. Now we're going to talk a little bit about what the process looked like, how it evolved over time, how we took this idea, seems simple and straightforward, maybe not simple, seems straightforward, and wanted to apply it to production, and some of the challenges that we encountered.
Okay, so our recipe says step one is start with a successful outcome. So so like what in Netflix, what does success look like?
Yeah, so this was a fun question to ask Peter. What is success?
Well, so when I did it in the lab, I was doing stuff over sort of distributed databases. So success was like a row that said it worked. There's a 0 return code or something. Well, you have return codes. You do like request response over HTTP, right? So why don't we just say if we send the client a 200, we're good?
Yeah, that's an option. We can see HTTP status 200. We can give that a shot. So we go out and we run some requests and we look at some things. Oh, yeah. Let me tell you about the dirty secrets of production. It'd be great if we all followed this convention and it was true all the time. But in fact, we have a framework within Netflix that purposefully always returns a 200 and wraps an error inside of it. So
why would you do a perverse thing like that?
It's production, man.
Okay.
So we kind of went back to the drawing board here and we said, okay, well, what can we use to measure success? So I want to draw on an Amazon leadership principle that I'm fond of. Start with the customer and work backwards. So when we're talking about what success means, we can talk about it in very concrete terms. Success means that our customers were able to do what they were trying to do, that they didn't get an error and that something didn't prevent them from doing it. In the case of Netflix, can they stream? So really, that's what we want to measure. So the nice thing is, within Netflix, that we have real user monitoring built into our client-side devices that propagate back up information to the service about successes and failures. And in fact, we were able to tie these in and learn about whether a specific request had resulted in a customer-facing error or things had gone wrong. If you've seen this screen before, I apologize.
Hi.
It might have been us, but I don't think so. So we want to catch those errors, and we want to find them, and we want to measure them so that we can have that feedback.
So we sort of solved the first problem that presented itself to us, and it's worth popping up a level and saying, like, what was the resounding lesson for Kolton and myself? And for me, it really had to do with when you feel like you're lost, start with something that you know. Start with the gold standard and kind of work backwards from that gold standard. Start in the middle of the maze and work your way out. And so for me, like in my academic idealized model of reality, it would never have occurred to me to have customers be like part of the model. But thanks to Kolton's insight, I'll never again look at systems like LDFI and fault injection in general without sort of contextualizing success in the context of observable results for end users.
And for me, working backwards from what you know, as I read the LDFI paper, as I watched Peter's talk, it was an epiphany moment. You know, I'm a pessimistic person. I like to think about all the things that could go wrong. Sometimes that makes it a little bit more complicated, a little bit more of an intractable problem. But you know, once Peter convinced me, let's start from what went well and look at what could have prevented it, that narrowed my vision and our approach, and it allowed us to take a more directed solution.
Awesome. So 1 down, 3 to go, right? So the next thing that we need is to be able to ask and answer why questions. What I would love is for you to tell me that Netflix has lineage. What have you got?
So you're going to be excited, because we do. We have tracing. It's built in, similar to Dapper or Zipkin. We have the ability to see where a request travels through our system.
Okay, sounds legit. Picture's worth 1,000 words. Let's stare at a picture. So Kolton and I spent a lot of time in front of the whiteboard, right? Pretty much every solution involved us staring at a whiteboard for a while and one of us saying, I've got it. So we're looking at the whiteboard. Okay, I buy it. So it's a request comes in, it hits API, and it calls out, fans out to some services that are required to satisfy that request, and then it fans back in. And in some sense, this is an explanation of how the system provided its expected outcome. And even nicer than that, in addition to being an explanation, it also identifies the inflection points, services, at a very coarse grain, where failures could have happened. So that's great. That's exactly what I wanted, except, yeah, so there's one wrinkle with this, right? Where's the redundancy? Remember that graph I showed you where like there's replica A and replica B? Where's the redundancy?
Yeah, there's not any redundancy in that graph. Yeah. I mean, granted, it's Netflix. We have redundancy everywhere.
I believe it.
Redundancy in regions, redundancy in hardware, even redundancy in code.
Well, so that's great, but I need the redundancy to be in the graph because the way that LDFI prunes that giant space of inputs is by recognizing the experiments it doesn't need to do based on the redundancy. So like we knew this might not work out. Like maybe we should just cut our losses here, right?
Game over.
Yeah.
Didn't work. It was a good shot.
Yeah, but it's 3 o'clock. I don't have to go home for a little bit. Let's like stare at this thing for a little longer. What could we do?
So what could we do? Well, we know there's redundancy. Like, let's just go break some stuff and let's see what happens. Like, we got some time. We got this request. We pulled up the graph. Like, we know it's there. Let's go break some stuff and see what occurs.
Let's break that thing.
All right.
Okay, so we break it. We run, and it doesn't result in a user visible failure. Okay. What it does result in is another graph. Okay, so I see what you did there. You didn't need bookmark to satisfy the user because you have a bookmark fallback. But I'm still not seeing any redundancy.
Well, but we know it's there. So what we need is we need to be able to learn about it over time. We know that the fallback is there. We know that get bookmark works. But we need to somehow put that all in one graph that we can solve.
Oh, of course. So like, I was coming with this model where a graph reveals redundancy. And now I'm given a bunch of graphs that don't reveal redundancy. What reveals redundancy is the site. Its behavior over time reveals its redundancy. What I need to do is think about these models of a system redundancy as being much longer lived, something that we build over a longer time scale, right? So in fact, very trivially, we could take both those graphs and route them under the same node, and now it would be a graph with ands and ors. Now it would essentially capture the redundancy of the site. And over time, we can just imagine enriching this graph as we learn about more successful executions despite faults. Yeah?
Yeah.
Oh, man. So I got to pay homage to Kolton on this one. I was so rigidly attached to my initial model of what a lineage graph looked like that even if I had somehow been given VPN access to Netflix and could actually look at these traces and look at these systems, it would never have occurred to me to kind of pop up a level and think about redundancy as something that's revealed over time in response to failures as opposed to in individual executions. So I got to hand it to you, man. And I like to think that this is the kind of thing that maybe neither of us would have been able to do on our own. This is like an example of that multiplicative effect that I was talking about. We're kind of starting at these two different poles and marching towards this middle point. And when we get there, we find that we have more than either of us brought with us.
And I think really Peter's too kind. As we're sitting here, as we're whiteboarding, as we're side by side trying to solve these problems, we discuss it, we debate it, we talk about trade-offs, we find something that'll work. And so this is exactly what comes of that. Some back and forth, this doesn't work, let's try this. We get some more information, and together we're able to find a solution.
Awesome. So now we're really cooking with gas. So the next part's easy, right? We just have to take that graph and extract the subtrees as I showed you. This is kind of my area. And I also wanted to prove to Kolton that I could write real code. So I said, I got this. I'll code it up. I'll code up the solver component. And so, I figured this will take about 2 hours. I started going. I installed IntelliJ. That actually used up the whole time budget, actually. And then I got Gradle working. Okay, so the next day, I'm like, okay, well, how do you convert a formula to CNF? This is undergrad stuff, right? So it's undergrad stuff, but it's still a pain in the ass. I had to write a lot of notes, figuring out how to distribute the ands over the ors, and so on and so forth, figure out how to do good commit messages. And so suffice it to say, after about 3.5 days of coding, I committed some code to the Netflix production repo. Code that I'm proud to say is running in production at a company right now.
Well, minus the print lines.
Yeah, right. I'm sorry about the print lines. So okay, that's done. And now it's just the victory lap, right? Because we know how to inject faults. We already got the great infrastructure for that. We can just hook right into the API. So it's just a matter of sort of doing a victory lap around this thing and replaying the interactions as many times as we need to either find a bug or, find more call graphs. What are you looking at me like that for?
Did you say replay?
Yeah, you replay the request.
Ooh, I don't know if that's going to work.
Why not?
Well, we're talking about a distributed system, requests that are hitting things all down the line. Who knows what's going to change underneath this? Who knows what kind of state is going to be mutated or things are going to change?
So just replay the gets.
Oh, so idempotence.
Yeah.
So we can leverage idempotence, right? Well, that sounds like a reasonable approach. Who thinks that would work? Yeah.
Oh, so many.
Smart crowd. Smart crowd. So,
oh, dude, why is reality so ugly? This is so messed up. And of course, yeah, it's not just a matter of the request might change something. It's like, what's the point of replaying requests? Because the services are changing under you all the time. Like one is reminded of another dusty old philosopher quote, that of Heraclitus, who said, you can never step in the same river twice. And that's not just because the river keeps flowing, or because the foot changes the river, but also because the foot changes, right? There have never been two requests in the history of Netflix that are exactly the same. So, we're fucked, right? This is a good time to cut our losses, right?
We had a lot of fun over the summer, can you tell? We hit some spots. Oh, man. No, I think we could solve this. What we need is we need to find a way that we can treat requests like they're replayable without actually replaying them.
Okay, can I whiteboard for a little bit?
Yeah.
All right, so what you're saying, interpreted through an academic lens, is that we have a bins and balls problem, right? And we have this infinite stream of requests, no two of which are alike. And what we want to do, though, is we want to group them into some finite and manageable set of equivalence classes among the requests, in which any two requests, if they map to the same bucket, we can treat the second one as if it was a replay of the first. We could simulate replay with some sort of fuzzy notion of fungibility. But that would require R and R prime to be the same according to some definition of sameness. What does it mean to be the same?
Well, let's think about that. I mean, we're doing failure testing, so what we really care is, do they fail the same? And in some regards, we want to know, do they behave the same? Well, if we think about it, we have these nice graphs that we already have that we're using to answer this question.
That's brilliant. It's almost like the same solution. So those call graphs that we used as a proxy for lineage, we can use as sort of a proxy label for the classes, right? If two requests produce the same call graph, then those two requests are sensitive by assumption to the same failures, right? So that's like a class label, but wait a minute, hold on. In order to do the injection and fit, based on what you told me about fit, we're going to need to sort of annotate the things right when they come in, right?
We have to make that decision as the request comes in with what data we have available.
Which means that we need to be able to predict the call graph that a request is going to produce when it fans out through the site before it fans out through the site. Which means, let's see, we need to learn a function, f, that we give it a request and it predicts a call graph. It sounds like a supervised learning problem, right? Woo!
Well, and Netflix has a lot of smart people that know way more about machine learning than I do. So let's go chat with them. And we go and we sit down and we start talking to them. And it turns out that we can't just say, hey, solve this problem for me and get back to me in 2 weeks. We have to do some work to make it work. We have to do some scrubbing. We have to make sure that the matching works correctly. We have to try different algorithms. And so what we found ourselves with was a problem, a conundrum. We could either solve the machine learning problem, which looks sweet and a lot of fun, or we could solve the failure testing one. And since the failure testing one is the one we needed, we chose that one. So what is the simplest thing that worked? So credit to Peter here, because I was a little disillusioned, wasn't quite sure how we were going to solve this. Peter goes off and dives into the data lake. He's walking through requests, he's walking through all sorts of information, and he finds that for a subset of requests, there's a pretty consistent mapping between some of the parameters we see in the request and the services that get executed. So great. if we just target these requests, we can find that mapping, and it will work well enough for what we're trying to accomplish here.
So lesson 3, and I'm going to go quickly because we're actually running out of time, was in large part a lesson for me, right? And I came to the table with these sort of pristine, idealized models of reality. And as much as I didn't want to let go of the simplicity, because simplicity is what makes a model good, it turns out it's a lot easier to adapt, to fit or retrofit a model to an extremely dynamic reality than it would ever be to do the reverse, especially in a summer. So what I had to kind of give something up, right? And this is like collaboration involves compromise, not just the kind of compromise where you just give something up, but where you give something up to get much more back.
And it's a great opportunity for us as well. We learn about how our models could be better, the data that we should be capturing, additional things that we could do better that would make it easier for us to solve these problems down the road. So, as Peter talked about, a simple matter of code, a little bit of time goes by, 2 or 3 months, and we go hack at it, and we make it work, is the long and short. We go through, we fix some bugs, we have some rendezvous problems with reporting customer data. We've got some, I'm an engineer, I wrote some bugs, had to debug them and figure them out. But, and I guess I kind of ruined this, doesn't work. I mean, obviously we're here, so we probably wouldn't be talking about it if it doesn't work, but it does. So let me tell you a little bit about the request, the case study that we studied. So at Netflix, there's a request that's called the app boot that happens at startup. It touches a lot of different services, and it sets up your session. It authenticates, it downloads some content, it caches things so that it's going to be a quick and important user experience. It's what Netflix calls a moment of truth. If you go to boot the app and it falls on its face, you're probably not going to be happy as a customer, and that's certainly not what we want. So in this case, we're talking hundreds of services that are touched in this request. As Peter mentioned, if we were to do a naive approach, we're talking a very large number of experiments. So I'm happy to say that we were able to explore this entire search space in 200 experiments. And furthermore, we were able to find 11 different bugs. Some of them single points of failure, some of them multiple points of failure, but bugs that would have been customer-facing, real bugs probably that customers were hitting.
So we both got what we wanted. Kolton found bugs before customers did. I got to argue that we identified bugs that another technique would never have found because of their depth and complexity. So, we did it. This is the part where we part ways, and our one column that we merged into kind of breaks off again into a duality. I'll go quickly through this, but obviously as an academic, there's a bunch of academic questions that I would like to ask, and I have, a sort of comfortably academic time frame to do them in. Our SAT formulation of the problem sometimes has a very large number of solutions, and they're not all equally likely. So in an ideal world, what we'd like to do is next time we use our fault injection infrastructure, we want to test faults that we think are the most likely ones to be tripped by customers. This is going to involve turning that decision problem into an optimization problem that tries to find the best next solution. This is hard work. It's going to take a few years and lots and lots and lots of money. Obviously, now I would like to be able to improve our tracing infrastructures to collect something that looks a little bit more like legitimate lineage in database systems. In particular, some of those services in that graph are stateful, and the explanation about why you got a response doesn't just have to do with that call graph, but it has to do with call graphs from the past that changed that state. Now, Kolton is extremely suspicious about, it thinks it's extremely unlikely that this is going to work in practice, that the overheads of provenance collection are going to be too high for industries to bear. But that's what makes it research. We also kind of we didn't look at time, right? We said what set of services fails. But in order to trip certain faults, we have to fail services in a particular order, which needless to say, vastly increases the complexity of the problem by a factorial figure. Thank you. Oops.
Yeah, so on the other end, richer device metrics. We're only capturing them for a subset of devices. We want more insight into what fails. This request class creation problem, it's not solved. It still needs to be done. Right now, we can only focus on a subset of the Netflix API. We can't hit all of it. And as Peter mentioned, we can do a better job in prioritizing how we search this space.
So I have a lab now and a team. It's called Disorderly Labs. You should visit our website. I have a bunch of brilliant students who are going to be working on this problem for the next 5 years at least, and then beyond that if I'm lucky enough to get tenure. So look me up, especially if you want to do these kinds of collaborations in the future. I have some good ideas still.
And so I left Netflix in January to found a company. One of the things that made this possible at Amazon and Netflix was the infrastructure that allowed us to cause these failures in production in a safe and deterministic way. Not everybody has this, but I think if everyone did, that they'd be able to do this better, more thoughtful fault exploration. In particular, Gremlin is built to run on Linux, has a command line interface that causes bad behavior, things like taking out CPU or RAM, mucking with network traffic. As we talked about an API, I think an API is extremely important. Who knows what's going to be built on top of it? And the ability to tie into your continuous integration and continuous deployment is what helps us prevent the drift into failure. Lastly, I think that good engineering tools need to be easy to use. If you want people to do the right thing, you need to make it easy for them to do the right thing. And so I'm a big fan of a simple, powerful web UI that guides users through understanding how to fail, what could go wrong, and helping them to understand it. Things like being able to schedule attacks, being able to configure it to confine that blast radius and the failure scope. And of course, the big red button that says halt all, because if things ever go wrong, you should just stop it.
So we should probably go fast?
Yeah,
You want me to take it,
mean,
or?
I think, we've talked through these lessons,
Work backwards. Meet in the middle. Adapt the theory to the reality. And if you take away one thing from this talk, because you fell asleep, and I'm sorry, this was a talk about putting together two things, right? And the metaphor that I like to use is that, we started at these two poles and we marched to the middle. What was interesting is, we started with all this knowledge, so we're like carrying all this stuff in our arms. And we had to make all these compromises along the way. So as we're marching, we're like dropping things. And yet somehow, miraculously, when we get to the middle, we end up with more than we began with. It's like some loaves and fishes kind of miracle. This is amazing for me. So academia plus industry can be academia times industry, right? If you're willing to make compromises, embrace risk, and march towards that middle point, right? We can build better solutions, which is what I think we succeeded in doing. So thank you very much.
Thank you.
Question.
We have time for questions? Obviously, the invitation's open to come and find me and Peter online, on Twitter. Peter's big on Twitter, or anywhere else, and come chat with us.
Really? No questions.
Go ahead. Gremlin's in closed beta. We launched closed beta on Monday. There's a handful of companies that we're working with. We're planning to do open beta come January 1st. If you'd like to hit our website, I threw some stickers around. If people like stickers. You can hit our website and sign up.
So how are you guys simulating things breaking in prod without actually breaking things in prod?
Great question. You should answer that one.
So that's where the failure injection infrastructure allowed us to. We kind of abstracted over it here. I actually gave a talk in QCon New York last year about that, if you want to go watch it. But the long and short of it is we're simulating failure at key injection points along the stack. So RPC boundaries, hystrix, if you're familiar with hystrix, persistence and caching tiers are great places to either inject a delay or return an exception or throw an error. And we had the people that own those libraries at Netflix write that failure code. So they did their best to emulate real production failures as close as possible.
I think this is maybe more on the other question, but like just logistically, how do you simulate? Do you actually have a test infrastructure that has every service running, or do you just find individually the points and just test those in isolation?
Oh, Netflix are cowboys. They do everything in production. And the reason that they can do it safely, as Kolton indicated, is that they can simulate failure at the granularity of an individual request without affecting the other requests that may be multi-tenanting on that portion of the architecture. So we're testing in production in the strict sense, but controlling, as Kolton said, the blast radius of what you could affect.
I think you guys are being able to grab those production issue information like the payload in order to do the analysis, right? And how does Netflix grab those production payload without affecting the performance?
Yeah, so 2 points. Fit is meant to be, short-circuited, where it's not going to do any work unless it needs to. If we've chosen to decorate a request with failure, we're okay with a small amount of performance degradation. It's one that we've measured and that was negligible. It didn't really show up in customer-facing
I think the question
graphs.
was about tracing, though, right?
I think tracing was an element of it.
So I think, in general, Netflix is using a system called SALP, which is an inheritor of Zipkin, based on Google's Dapper. So it's doing this at sample rates that are completely controllable to trade off between observability and overhead. And things like Zipkin, open tracing, are becoming an emerging standard. That is, you're beginning to be able to expect that large-scale microservice architectures are collecting traces of this kind, obviously at a fairly low sample rate.
Do you have a sense of the financial value of this investment in quality?
Ooh, call on me. I think that I love to ask, what's the cost of being wrong? What's the cost of downtime for your company? If you work at Amazon and you're down on Black Friday, it's measured in hundreds of thousands of dollars a minute. So I think that's really what you have to. That's really what you have to do. And if you want to go convince your management that failure testing is an important investment, not just for the training or the operational burden reduction, you make it about the money. What does that 9 cost you? And that doesn't even count the cost to your brand, the cost to customer trust.
Do you have some examples of a bug that you found with the system that you could not have found with engineer-guided? Because you're obviously doing a lot of failure testing already, but engineer-guided. So, do you have a specific example of why you found it with this that you couldn't have found it with engineers?
So we did a lot of our proactive failure testing at the failing one thing at a time. There's so much low-hanging fruit that just failing a single component tended to keep us busy. Some of the bugs that we found in app boot involved 3 and 4 services failing together.
Yeah. So what I would add on to that is that a lot of the sort of engineer-guided stuff is focused on whether the sort of solipsistic view of a service and its immediate dependencies, and is the service robust to failures of its immediate dependencies or something like that. You can go a very long way with that. But it's also true that correctness is really an end-to-end property of a whole user's interaction across many microservices, and it's by no means trivial to sort of stitch together and compose the expertise of the individual service owners to reason about what could go wrong sort of transitively. And that's why it was so important for me to find not just to count the bugs that we found, but to illustrate that some of them involve these non-trivial compositions of multiple types of faults that would involve the expertise of many service owners who don't really know the totality of that graph.
And I'm sure, as you know, being from Uber, at scale, you see not just single failures, but combinations of failures. And some of the worst outages are 2 or 3 things that you don't expect to go wrong at the same time.
Yes. Thank you.
All right, thank you.